Hi there. The title is as on the screen, questioning whether we really do see human-level object classification performance in deep neural networks. So I'm going to start with some ancient history, my own childhood. When I was a teenager, I read this book, The Computer and the Mind by Philip Johnson Laird. I was already quite into computers and artificial intelligence. And this book, more than any other single thing, convinced me that the study of psychology was essential to the development of artificial intelligence. So I did an undergraduate degree in psychology, and as a result, then did a PhD in computational modeling of categorization. Well, back then, and I got my PhD in the late 1990s, AI systems for object categorization were fairly unimpressive. There were systems that were able to automatically recognize handwritten single digits to human levels of accuracy, but that was about it. So I ended up spending the next couple of decades trying to better understand how people categorize things, with an undercurrent there that one day the technology would catch up sufficiently to make use of this information. Now, a few years ago, I became aware that some computer scientists were now claiming human levels of accuracy in object classification for their AI systems. This claim seemed worthy of investigation because it seemed to me like there were two possibilities. One was that the claim was well-founded. These systems really were at human level now, in which case there might be utility in these AI systems for understanding how people classify objects. Because as far as psychologists are concerned, we don't really have a good model of that. If there's already an artificial system that can do it to human level, maybe that's interesting. Of course, the other possibility is that the claims about the artificial intelligence systems were overblown. In the history of artificial intelligence, this is not unusual. If people are in fact still substantially better than machines at object recognition, then maybe psychology can help characterize the sources of the differences and help us build better AI systems. So what do these modern AI systems for object recognition look like? Fully getting this across would be a talk in itself and a much longer than a 20-minute talk. So for now, I'll just aim to get across two key ideas. First, they are associative systems. Now, the Rescorla-Wagner model, which has been with us since the early 1970s and is covered in many undergraduate psychology courses, including this one, is a simple associative system. It has input representations on one level, for example, of tones and lights and so forth. And these are linked to output representations, for example, food, with connections of varying weight. And that weight is adjusted by a learning rule. That's a shallow neural network. The Rescorla-Wagner model then, with its one layer of weights, is a shallow system. Modern object recognition systems, however, have multiple layers of weights. Now, there's nothing particularly new in this idea. Psychologists have been using such systems since the mid-1980s for modeling. For example, psycholinguistics. In psychology, this general approach became known as connectionism and became rather popular from the 1990s onwards. Now, these systems with multiple layers of weights are known generically as deep neural networks. And two layers of weights as shown here is a minimally deep model. Often they have many, many layers. However, in addition to being deep, the modern systems that are used for object recognition in AI take inspiration quite directly from the known properties of the early visual cortex. Again, as covered in most undergraduate psychology courses, early visual cortex is made up of neurons that pull information across increasingly large areas of the retina. So you have V1 neurons that have rather small receptive fields, which then feed into neurons further down the string. Modern object recognition systems follow this sort of architecture quite directly. And this sort of system is what we call a convolutional neural network. The word convolutional here is obscure and less you have a sense of the mathematics being used, and so just use it as a piece of jargon term for now. So these are convolutional neural networks, and these are the sorts of things that engineers are claiming now have human level performance in object recognition. So how good are these systems? Anecdotally, they're really good. There are plenty of examples from about 2014 onwards of both software engineers and neuroscientists claiming that human level performance occurs in these systems. So the next slide shows a typical quote from a couple of rather prominent neuroscientists. So they say, recent advances from machine learning led to the discovery of a hierarchical neural network model that achieved near human level performance on challenging object categorization tasks. So that's 5 years ago. That's the sort of system we're talking about. And the claim here is that we've already reached human levels of performance, say about 5 years ago. Okay, so that seems like quite a strong claim, and it's the sort of claim that really caught my attention. Can we be any more specific? Can we put any figures to this? Well, yes, we can. A relatively recent system called PNAS-Net scored over 95% accuracy on a very large database of images drawn from the internet. Now, this sounds pretty impressive until you notice that top 5 condition that I've written on the slide there. To explain this, when the model is presented with, say, an image of a cat, we look at the 5 things the model thinks it's most likely to be. Now, let's say the model says it's most likely to be a hat stand, and if not, an orange. But if it's not that, then maybe a battleship. But if not, a dandelion. But if it's not any of those, then I guess it's a cat. Well, that answer counts as getting it right. That's a top 5 accuracy, because it was amongst the top 5 things you thought it was. Now, from a even vaguely psychological perspective, that does not seem like a particularly good definition of getting the answer right. A more realistic answer comes from what's called top 1 performance, which, as I say, is also known as, well, getting it right. On this basis, the top models currently get about a quarter of all the images they're presented with wrong, which doesn't necessarily seem that human-like. We would have thought intuitively that humans would be close to ceiling on a task like this. But actually, that's not the end of the story. The performance is not as good even as it appears on this slide. All of these systems have been trained on very large sets of images. In order to create such large sets, engineers just trawl the internet automatically. And that's all very well if the internet contains a representative subset of the objects in our world. But the evidence is that it doesn't. Now, Andrei Barbu and colleagues working at MIT took what I think is quite a psychological approach to this problem and collected a much better controlled set of images. They did this by directing people via their mobile phones to take pictures of objects at a range of different angles and against a range of different backgrounds in their normal environment. Now, the resulting set of images look anecdotally like people would not have much trouble classifying them. You can see some examples in the slide where the chair on the left is from the sort of set that was used to train these network systems, and the 2 on the right come from Andrei's test set and were taken by participants in their own homes. However, what you can see as well from this slide is that the computer systems do appallingly on this more representative subset. So whilst they're about 72% top 1 accuracy on the internet objects they were trained on, they're only about 30% accurate on objects from this transfer set with things taken at different angles against different backgrounds. Which leads us to my next question, which is, well, how good are people on these better controlled images? The next slide is a little small, I'm afraid, but and maybe that accentuates the point. These pictures are well controlled, but perhaps they're not as simple as the ones the model was trained on. You know, they're atypical angles, they're cluttered backgrounds. So maybe people wouldn't be better than about 75% correct on these either. How do we answer this question? Well, the first thing I want to say is that software engineers are not often psychologists. So it's perhaps unsurprising there's little good data on this question about human performance. I mean, I guess I could go on for a bit about the ways in which the published attempts by software engineers to assess human object recognition performance fall below the standards of professional experimental psychology. But that would not be particularly productive. Instead, I'd like to tell you about some data we've collected on this question. The data I'm going to tell you about was collected by Sherry Neal and Annie Marriott as part of their undergraduate dissertation. They also did a first pass at analysing the data, but there's some issues with that analysis, due to some problems in the experimental code, in fact. Gottschalk Kuhl, who started as a PhD student in my lab back in April, has reanalyzed these data, and it's her analysis that I'm going to present today. So in this experiment, we chose 10 categories of object from Andre Bardou's set. So this is the set that people were taking with their mobile phones around the house. We didn't pick 10 categories at random. Rather, we picked 10 categories which, on the basis of simulations run by Andre, were amongst the hardest for modern object recognition systems to identify. The system was one called ResNet 152, which is a standard modern system from Microsoft. Now, as you can see, I've just given one example here, but you can see from on the left of this slide, all the categories we chose were pretty everyday types of category: baskets, candles, plates, umbrellas, and so forth, which, you know, a priori, we would think people would be reasonably competent at classifying. Now, for each of these 10 categories, we sampled 30 example pictures, giving us 300 images in total. Each image was presented for a fixed amount of time and then removed. The participant then has as much time as they like to make their selection by pressing the appropriate number key. The numbered list remains on the screen when the picture disappears, so the performance on this task is presumably driven mainly by object recognition performance rather than, say, difficulty in using the response system. In this experiment, we used two different presentation times, 200 milliseconds and 1000 milliseconds. The relevance of 200 milliseconds is that systems like ResNet are feed-forward only. The brain's visual system, however, is recurrent. In other words, it has feedback links as well. Information flows in both directions. But at 200 milliseconds, there is little time for recurrent activity in the human brain. So that short presentation time, to a first approximation, reduces humans to an approximately feed-forward system like the computational systems we're comparing them to. Now, we chose 1000 milliseconds as a longer interval comparison, so we could see what happened when people had more time, but we kept it to a second just so the whole experiment would fit into 30 minutes. We tested 50 people. This was all done online using Open Sesame and JTOS, with the participants being psychology students completing for course credits during a pandemic. No feedback was given, so participants received no explicit information about their levels of performance. So it's probably reasonable to say that our data don't represent the upper bound of how well people could do on this task. More like how well they do when perhaps motivation, at least in some cases, was pretty low. Nevertheless, as we can see from this slide, people were way, way better than a leading AI system. The blue bars here, somewhat misleadingly labeled as ObjectNet, are in fact the performance of ResNet 152, a leading AI system, on these 10 categories. Now, the comparison at this stage is only approximate because the ResNet results come from Andre's paper and are hence assessed against all the images in each set of his category, rather than the subset of 30 images per category that we showed our participants. Nonetheless, it gives us a ballpark figure for accuracy And that is that ResNet is between 1% and 13% accurate on these categories, depending on which category you look at. Now, looking at the green bars, you can see that even at a 200 millisecond presentation time, people are much better than this, generally between 80 and 90% accurate. An additional 800 milliseconds of presentation time improves accuracy by a few percentage points. Probably it makes sense in future work to extend presentation time beyond 1,000 milliseconds, perhaps including a self-paced condition with motivation to perform well. This would give us data on the upper bound of human accuracy on this task. Similarly, 200 milliseconds seems to be a lot of time for these categories. Performance is pretty good. Perhaps reducing presentation time further down to, say, the subliminal threshold of 50 milliseconds or so seems another reasonable target for future work. And of course, it would probably make sense to expand the set of tested categories such that they sample across the full range of difficulty for the machine systems, rather than just picking the ones the machines found hardest, as we did here. So I just have a few minutes left. And so in those, I guess about 3 or 4 minutes I have left, just like to reflect a bit on why these computer systems, which at first sight seem quite good and also quite neurally inspired, are so brittle. In other words, they break so easily when presented with things slightly different to what they were trained on. I said a few minutes ago that one difference was that the machines are feed forward, while the human brain also has feedback connections. This, of course, may be part of the answer, but the high accuracy people show at 200 milliseconds suggests that even the feed forward part of the human system well exceeds machine performance. So what are the machines doing wrong? Well, despite superficial similarities, these systems are not currently that human-like. For example, for humans, the overall shape of an object is among the most important things that identify it as that object. The silhouette at the top left is clearly a camel. The one on the bottom bottom left is not a camel, or at least it's a horribly injured or deformed one. To the machine system, however, these are equally good examples of camels. You can see also similar patterns here for, say, the microphone, which is also quite striking. Another example of problems with these systems, or perhaps the other side of the same coin, is that these machine systems have a very strong prior to select the simplest possible solution. So in the study on this slide, the images the machine is trained on have a single pixel, which isn't visible on these slides, but is there, a single pixel that perfectly predicts the category membership of the item. This system trained on this set correctly classifies all the 4 objects in the left-hand column as an airplane or aeroplane, if you're English. And these are ones where that single pixel is preserved. However, on the right-hand column, it gets all the 4 objects wrong, calling them a cat. And this is where we've changed the single pixel to the one that predicts cats in the training set. Now, even if you take out that misleading pixel and just leave a blank where the predictive pixel was, the network still drops off a cliff in terms of accuracy. So it was really heavily relying on that one highly diagnostic but very minor part. So presumably people would be at ceiling on both of these sets of images. So I think one direction we need to go in terms of the development of these machine systems, is to work on making them less brittle. And the human brain seems like a pretty good exemplar of a system that does not break so easily as the machine systems. I only have about 1 minute left, so just very briefly, a couple of directions one could take. First, there's some work here by Tzvetkov, I think, who've attempted to build machine systems where the lower levels of the network are more directly modeled on the known properties of early visual cortex. And that seems to be producing some better results. And another direction by Dagaev, I think, who have attempted changing the learning rules in the systems to include a too good to be true prior. In other words, the model instantiates the belief that very simple solutions are also very unlikely. Again, it seems like that might help. Right, that's about it. thanks for listening. And why not join us? There's a great deal of work to do here in bringing psychology and computer science together on object recognition. But the consequences of doing so could be quite good. Right. I'm happy to take questions.